Good afternoon, everybody. This is Peter Coombs, and as I just like to reiterate Tom's welcome to you all. This is the third in the series that we've been running through in the last sort of 6 weeks or so on how you can go about designing these sustainable drainage systems throughout the Middle East using the MicroDrainage program. The main thing today is looking at how we can go about designing these drainage structures, but not just in isolation. The whole purpose of this exercise at the end of the day is to complete a fully integrated model. So welcome for those that haven't made the first two presentations, by the way. We will be recording these presentations and uploading them. It's just lack of time right now, so we will get onto that case and get them uploaded over the next 6 weeks before the next webinar. But the idea is to completely fully integrate the model. The first webinar that we ran looked at the planning, so we could scope out where these structures would best sit. The second webinar was designing the integrated the flow conveyance system, the stormwater and the foul water networks. And now what we're going to do is we're going to design these structures which we can then add into the model. This is the purpose of the exercise today. Now, I will be working in a module called the source control module, and what we'll do in there is to carry out storage estimates, we'll design structures, but then we can cascade them together and test this SUDS train, as we like to call it, for the hydraulic performance, but even more importantly sometimes the water quality performance. So you can start to feel the difference between what you can do with the MicroDrainage software in terms of modeling and water quality that you can't maybe do with other programs, or you have to do something with an Excel spreadsheet. So the idea is to run through this systematic approach. As I mentioned, the first webinar was on the planning side of things. The second webinar was looking at the design, and then the third one today is design the structures and modeling. And I'd like to thank Nadine Batar, because for those that are doing, and we're doing this throughout the Middle East and have been since 1991 as it happens, but for those that haven't done this so far, this is a prerequisite, it is a requirement, and the standards are coming through from the municipalities, from the public works departments, the visionary documents that are cascading down now up until the year 2020 or 2030. This is the way forward. So if you haven't done it already, you will be doing this very soon. And we'll be using the MicroDrainage program, and as I mentioned, the source control module is going to be the sort of mainstay of the presentation in the initial stages, and then integrating the model with the full network towards the end, although I will show you the network at the beginning as well. So what we're trying to do at the end of the day is provide these multiple benefits in an affordable way that will be compliant and robust, but also maintainable. So without further ado, let me go into a live demo with the software. And as I mentioned, I will be going through source control and looking at storage estimates. There we are. Just to set the scene, as a reminder for those that attended the previous events, what we have done previously is to design these stormwater and foul water flow conveyance systems, and the purpose of the exercise today is to now focus on these structures, whether it be a pond or cellular storage or infiltration trenches, trench soakaways, etc., as Tom mentioned. And what we can do is, once we have fully integrated these into the model, is test them. And this is one in true Blue Peter fashion of one I've done earlier. So now we can see the flow coming through the flow conveyance network and even filling up the structures in this three-dimensional view. And this is the kind of end result that we're aiming at today. So to get there, let me go into the source control module. And when we open up the source control module, this would be the welcome screen that you would see. And to help with this systematic approach, we have a built-in design guide for you. So if I click on the design guide, we can see that on the left-hand side of the screen, there's a sequence that I'm planning to run through here. We can do a quick storage estimate. We can then do an estimate actually for the whole site. Now, the project that we just looked at, the overall site area is around about 10 hectares, and the impermeable area within the site is just under 5. It's actually 4.896 hectares of impermeable area. And we have a limited discharge provided to us of 50 liters per second. So first step, let's look at how much volume of storage would we need under the ground to make sure there is no flooding for the 50-year event for this particular site. And this leads us straight into the rainfall criteria. Now, after the first and the second webinars, there were a lot of questions about how do we generate rainfall profiles, how do we set up the characteristics for our particular country, and this is the how do I bit of the rainfall that I'm going to show you now. 2 steps. The first step, you need to identify the IDF information, the intensity, duration, frequency curves, basically. So if I click on the IDF editor here, the program will prompt us for information. So you can bring the information in a 1-minute time step, a 2-minute time step, 5-minute time step, or an IDF series. And it's an IDF series that we really are looking for. And that means we're covering a range of storm durations to ensure that your structures and your models will be robust for future extreme rainfall events, covering each and every storm duration. Again, this is something quite unique to what we're doing within the software. So we could have that information and physically type it in here. I could click on the cells and I could type information in, or I can load one in and I have a sample for a 50-year return period wherever my site may be, Riyadh or Doha, whatever. So I'm bringing this in, and you can now see the rainfall intensities in millimeters per hour against a series of storm durations. So these are average rainfall intensities based on a storm duration. That's generating a curve which we can now accept. That information is now in the program. Now, how does the rainfall land upon my site? This is the hard part. So typically, the IDF information is fairly readily available, and bless you all for sharing that information from around the region with us. We will try to put up a library of that IDF data, but the CRP, the cumulative rainfall profiles, this is the shape of the rainfall, the nature of the rainfall landing on the site. It's very, very difficult to obtain across the region. So if I click on the CRP editor, again, we could type in information. This is dimensionless. This is just providing the nature and the shape of that rainfall landing on the catchment. So you have a range of different options here. I'm going to load one in. And I'm going to load in one of 2 standard profiles that come with the software. Is a 50 percentile or a type 124. So I just want to encourage you all to discuss this with your clients, because I want this information to come out of research for the Middle East. The problem we've got is that you're not blessed with very much rainfall in the Middle East, so therefore there is very, very little information because of the lack of rainfall. But when it comes, it's coming in spades. So we need to capture that information and identify the nature of it. Now, I know within the region there are people using the 50 percentile, which is by clicking on that information and showing you in the spreadsheet form, when you reach halfway through the storm event, half of the rainfall has landed. It's a kind of a balanced parabola. This may not be your personal experience, but this is what I know people are using in the region. Okay. So with that information in there now, we can ask the program to tell us how much volume of storage we need for the whole site. And how big is the site? In this particular case, it's just under 5 hectares of impermeable area. So I'm going to put in the figure of 4.896 hectares of impermeable area. I can read this out of the MicroDrainage program when I've designed the flow conveyance system. And we're being limited to a discharge off the site to 50 liters per second. Now, if you're working in Qatar and even in Saudi, but mainly in Qatar, there is a specific requirement for you to carry out your design of infiltration systems in accordance with BRE Digest 365. This little calculator button is prompting you to input information as per BRE Digest 365. So what you need to do is on your site is dig a test pit, and this test pit needs to be at least 1/2 of a cubic meter in volume. Ideally the depth of the storage structure and roughly the size of the storage structure if it was a soakaway. So at least a meter or two deep, depending on the top water level that you're contending with. And then you fill this test pit with water and let it drain down a couple of times and measure the volume of the test pit and put that volume in. In this case, I'm going to stick in 1 cubic meter. So let's assume this one's a couple of meters deep, 1 square meter on plan. How long does it take for the water to drain down between 3/4 full and 1/4 full? Could be an hour, could be 2 hours, whatever you measure on site. And then what is the wetted area of the pit when it's half full? Well, if this one's 2 meters deep and 1 square meter on plan, the wetted area would be 5 square meters. And the program has now calculated the infiltration coefficient in accordance with BRE Digest 365 at a rate of 0.2 meters per hour. And we can accept that figure. Now, when you site your structure, what would the consequence be of it flooding? The lowest factor of safety, which is the next cell I'm looking at, is 2 that we would recommend using in the program. You can see at the bottom it's saying you can put anything between 1 and 50. That's what we would allow you to input into the program, but we would recommend at least a safety factor of 2, and then it ranges up to 14 depending on the severity of flooding. So if you sited your structure and it flooded and it adversely affected the entrance to a business, then that would be a safety factor 14. We run through this in the training courses. That's all we need to add in here. At this minute in time, we're not being asked to look at climate change and in terms of designing it out. We are in terms of testing it, which is the 4th webinar that I'll be running next month in July. So let's analyze this information and see what kind of volume we would need for this overall project. And you can see now that we have 2 distinctive ranges of information. Should we not choose to infiltrate into the ground, if you just use attenuation structures, storage structures that are lined, then you would need between 9,288 and 15,500 cubic meters of storage beneath the ground. That's a lot of cellular storage. Okay, so the average figure, well, first of all, why is there such a big range? Well, at this minute in time, the program itself does not know what type of structure we're choosing to put in place. We don't know what type of flow control. That's a really important factor, the nature of controlling the flow. Tom's got a question for me.
Yeah, it's just been asking you to comment on the default impermeability factor of 0.75. Is that something you would alter prior to running the rest?
Yeah, okay, so there's a default factor, the impermeability factor of 0.75. You could set that to 1, so essentially 100% of the impermeable areas, or everything that I'm putting in here, is 100% impermeable. And then let's analyze that. Yeah, the volume will start going up higher. So if you're truly taking every single impermeable area into your storage structures, then that would be the figure that I would put in, the impermeability factor of 1. Okay. Exactly. So as Tom mentions, when people reduce that factor, it's because they are aware that in the region you would have a very high evaporation rate. You would have areas of depression storage. Not every single drop of rainfall that lands on the impermeable area will actually enter into the network. So you may end up with a lot of attenuation even on the roofs of buildings, for example. So a lot of villas have flat roofs, and you'll have water 100 millimeters depth or whatever, and then that will evapotranspirate away and provide this depression storage. So if you want to err on the really safe side, you put the impermeability factor in of 1. That's giving you the worst case scenario. And if you have local knowledge or local requirements that say, yeah, we know that 75% of the rainfall actually landing on the impermeable areas will enter into the network, then you can reduce that figure down. The key thing here is that you can see that by just attenuating, we need, in this case, something like 17,000 cubic meters of storage beneath the ground. And when you know how much it costs per cubic meter to store under the ground, you can apply that to these numbers to see the costs of the flood mitigation measures if you attenuate. Now, this is assuming that we ignore the opportunity to infiltrate into the ground, and that the ground condition is common across the site. So you would have to run those test pits, those percolation pits, across the site to make sure that this is valid. But look at the lower figure. We're down to between 2,000 to 8,000. So, you know, we're down to 5,000 cubic meters of storage rather than in excess of 15,000 if you attenuate. Okay. There's a good question here. Does the program assume back-to-back storms? No, it doesn't, but we could run back-to-back storms with continuous rainfall and have 2 events, one leading after the other. However, what we do, and we'll see this in the next screen, when we're designing the structures, we analyze the half drain down time. So this is again Syria guidance, BRE Digest 365. This structure, or these structures, must half drain down in time for the next event, within 24 hours basically. So there's a half drain down time criteria. We'll see this when I say OK. So we can set up back-to-back designs, and we could set up a rainfall profile to run one straight after the other if we wanted to. So let me click on the quick design, and because we're running through this process, this systematic process, using the design guide, the information that I've inserted in the quick storage estimate has been remembered. So you got the little tick there, and there we're looking at a quick design on an infiltration structure. So for the overall site, we've got something like 5 hectares, in this case 4.896 hectares of impermeable area. Now the question comes, what structures do we want to use, and where do we want to locate the structures? Now, from the very first webinar, this is why planning out and deluging the site and looking at the ground model and seeing where those areas of depression are lying would help us maybe scope out the locations of a range of structures. I don't really want to just have one structure at the downstream end. I want to go right back up into the site and have a range of attenuation or infiltration structures scattered around the site, so we're holding back the flows, slowing down, and really just putting in a lag time and treating all of the rainfall back at source as best we can, and then on a site level, and then certainly at a regional level when we're putting in the the larger structures. So for this particular site, let's split it down and say that I don't know, 10% of that, so 0.5 hectares a half of a hectare impermeable area is now going to be treated by, and one of the most popular requests was cellular storage. So let me click on the cellular storage structure. I've clicked on the drop down to show you all the different types of infiltration structures that we could design within the program. We also have attenuation structures as well. We'll see that in a little while, but these are purely those that could infiltrate as well as attenuate, because we could switch off the infiltration coefficient. But line soakaways, house soakaways at a local level, infiltration trenches. Basically, this is a trench just filled up with a porous material, so no pipe, almost like a filter drain. Kind of a criteria for the highways guys out there. A trench soakaway would incorporate a pipe within the porous stone as well. We can design swales on the surface, so a ditch or a channel that would infiltrate through its base and indeed through its sides if you wanted to. An infiltration basin, that was one of the questions that came up earlier on. We could choose an infiltration basin. An infiltration blanket just below the surface, a depth of stone, of porous stone. Porous car parks, not really something I'd recommend over there because of the fines and that sort of problem of potential clogging. Complex structures has been asked as well. Yeah, we can design a complex structure. It's a good question, thanks for that. I'll show you a complex structure in my Blue Peter model that I'll show you at the end. So that's a very good question, because we're looking at these particular structures in isolation, but maybe you have a range of them on top of one another. So you may well have a basin. Beneath the basin could be an infiltration blanket, and then beneath that blanket could indeed be a trench or something like that. So you can build up a complex structure as well. Good question. Dry swales, this is essentially a ditch or a swale with a trench underneath. They've been seen to be very successful generally as well, rather than just having the channel. That's a trench filled with porous stone or something beneath it, and the filter drain, as I mentioned before, maybe sand filled. So for the site, this is around about 10% of the total area of the site. Notice that the infiltration coefficient has been brought through. So let me choose cellular storage was the most popular choice. So thanks for that, folks. Would we like to set the porosity value to the default for this structure? I'll say yes. You can always change this, but if you accept the default being 95% porosity. So 95% of the cellular storage structure is open and porous. We can see that we have infiltration through the base, through the bottom of the storage structure, as well as through the sides. And what you could do is you could switch off the base, or you could switch off the sides, whichever way you wish to work with this. I'm going to leave them both on. So in other words, when the storage structure fills up with water, every few seconds we're analyzing this. As the water level rises, there is infiltration going out through the base and out through the sides of this structure into the ground. The safety factor, I accepted at 2. If I sited this cellular storage structure in a position where it could create a nuisance, if it flooded, then I'd have to increase the safety factor, but I'll leave that at 2. And we could just design this literally in isolation and size it up so that there was no positive outflow. And thank you again for all the questions saying, how do we design positive structures? How do we design negative structures? Can we combine positive and negative? Yes is the answer to all 3 of those. So we're going to add in a flow control coming out of this structure, but it doesn't need to be restricted to the 50 liters per second for the overall site. This is around about 10% of the area, so let me limit the discharge to about 10% of the discharge rate, 5 rather than 50. And then I'll click Analyze. So just to remind you where we are, we're now just looking at optioneering. So we've carried out a quick storage estimate, and that quick storage estimate was for the overall site. Now we've looked at the sub-catchments of the site, and we've chosen, in this case, a cellular storage structure for about 10% of the area. And how big does it need to be? How deep and what sort of area would it need to be to work? And this is answering the question about the one storm coming in after the other. We look at the half drain downtime. What happens about one event running after the other? This is the importance of the half drain downtime, shown in the right-hand column here. So the structure must half drain down within 24 hours. So this is 1440 minutes. If we had anything longer than 1440 minutes, it would obviously show you the number, but show up in red as well. So this is essentially telling me that any of these options would technically work. Also be aware that we need to have ideally a meter of clearance between the invert level of your structure and the top groundwater level. Okay, so this is to allow the water to infiltrate down and for you not to be adversely affected by high groundwater tables. So that is really the key thing here. So how deep could we put a structure in place? Sometimes the top groundwater table, you could set a datum level there, add a meter to it, and then that's the invert level of your structure. So it's telling you what the options are here. So let me choose a 1 meter deep cellular storage structure, and then the area of it would need to be about 650 square meters. Yeah. Okay. In terms of evaporation, that would be the impermeability factor. You would reduce the 100% runoff. So if you had 2% evaporation, 11% evaporation, that's a potential to be able to reduce that from the impermeability factor. Within the porous paving, you can actually add in an evaporation coefficient, or evaporation percentage rather. It would be something probably like 11% in the Middle East. So that would happen in the permeable pavement option because they're typically very, very shallow. Okay. Now looking at the options here, I'm going to choose the 1 meter deep option, and then we need something that's going to be about 650 square meters in plan. And that's all I need to do here. If I say OK to that, then I'm going to click on Detailed Design, and let's go through the actual process of designing the cellular storage structure. So the rainfall data is the rainfall data that we set up in the first place. Is there any other additional flow coming in? Is there a hydrograph coming off of the natural landscape? You can incorporate that if you wish to. In this case, there is nothing. I'm trying to keep this relatively straightforward. We're going to design a cellular storage structure, but you can see all the options that we have available here, including the attenuation structures that could be pipes or culverts or tanks or ponds, etc., etc. But it's cellular storage is the most popular choice there. What about the outflow control? This is one of those key factors that would dictate the actual size of the underground structure. Now, a weir as an outflow control is not particularly efficient. So I'm going to choose, so I should have asked the question really, but I'll choose a flow control, and you can see the choice is quite extensive. I know that the guys tend to use hydro brakes over in the Middle East as a preferred choice. We could put in an overflow as well. Should this structure go beyond the design, the 50-year? What do you want to do? Do you want to control the flow? Ideally, yes. I'm going to keep this straightforward and say no overflow control. In this case, just to reduce the time, because I'm really conscious of the time rushing by right now. And I'll say OK to this. Do be aware that you could add in for climate change if the clients are asking you to design this in. It's an option. What's a hydro brake? Okay, very good question. It's a vortex control which is extremely efficient. I'll show you another animation next week because I'm going to run auditing, and I will show you that. Sorry, not next week, but the next webinar. Essentially, it is a control device that will allow the maximum amount of flow up to the 5 liters per second to be released to reduce the volume of storage that you need to provide upstream. So it's a very efficient way of adding in a device to maximize the use of the attenuation but reducing the volume, reducing the cost. Okay, this is the rainfall. It's prompting me now for the rainfall and network details, and this will run the shortest and the longest storm duration. It's running all of the events. This is the key thing. Now, time area diagram. Remember last time we designed the flow conveyance system within MicroDrainage. Within MicroDrainage, we could import a time area diagram. So the program knows essentially the time of concentration at every part of the network. We could import that. And this is essentially telling the program how quickly is the flow entering into this structure. And we've got 0.5 of a hectare. So I'm going to put in 5 time steps of 0.1. But as I say, within the program, it will tell you this to 3 decimal places. So we could export that. I'll show you that in a future webinar. Okay. So if I say OK to this, we've added in the 0.5 hectares of impermeable area, and we're telling it how quickly it's arriving. Okay. Now, what is the cover level? The depth of the structure is going to be 1 meter. I want to have that at least a half a meter, maybe 1 meter below the ground, and maybe the cover level is 5 meters above sea level. So if I take 1 meter off for the cover and 1 meter off for the structure, the invert level would be down at 3 meters above sea level. Okay. We've got the infiltration coefficients, the base and the sides brought through, the safety factor, and the porosity of the structure itself. And now we can tell the program that the structure will be 1 meter deep. We can click on this and put in an area. I think we need about 650 square meters of it. Okay, 650 square meters of it. When we get to the meter, I can close this off and say, look, just go 1 millimeter above the structure and then bury it under the ground. Yeah, so the question is, you know, we're building this structure that's infiltrating into the ground, plus we've also got a flow control. So what is this? Is this an infiltration structure, or is it an attenuation structure? And the answer is it's actually acting as both. And you'll see this when I've run the analysis. Bless you, Tom. When we see the analysis, we're allowing some positive discharge, but no more than 5 liters per second through the flow control. The rest is infiltrating into the ground. I could have designed this with no flow control and just sized up the cellular storage to infiltrate into the ground. Or I could have switched off the infiltration and just had it as an attenuation structure with a limited discharge. I'll show you this graphically when we've completed the design. Now this particular storage structure is going to be square. So when I click on square, this is now calculating the surface, the infiltration area in contact with the ground. Okay. And then the final part of the equation is choosing a flow control. The hydro brake, as I mentioned, the latest version is the Optimum, which was released fairly recently. So that's within the program that will provide you with the option to minimize your volume within the storage structure. Here are the original hydro brakes. So I'm going to put in the invert level at 3 meters. This is above datum. Maximum design head acting on the flow control is 1 meter. There's the flow curve for the hydro brake, and we can choose one. This is the stormwater system, so I would choose a stormwater only option, MD5 or MD6. And this is interesting because what it's showing is the MD6 is going to have an opening size of 93 millimeters. If you were to choose an orifice rather than a hydrobrake, the flow control opening size would be far, far less than 93 millimeters. It's probably going to be about 30 or 40 millimeters. In other words, there's a risk of that blocking. So that's another good reason to use a vortex control, is that you have a larger opening size, so you should have less problems with maintenance. So we all know what the problem with maintenance is everywhere, not just the Middle East. Now I'm going to say OK and accept these values. The screen will go blank because all the information has gone into the program, and now all we need to do is analyze this and then see whether it works or not. And I'm going to save this as a 0.5 hectare cellular structure number 2. The question is, depth is from the invert of the structure up, so you could read that to be height of the actual structure from its invert level, rather than the depth of the structure from below the finished ground level. Okay, so it's essentially the height of the structure from its invert level to the top of it. So really we've got 0 depth is down the bottom here, 3 meters above datum, but at the bottom of the structure, and then the 1 meter is the 1 meter height of the structure, and not the FGL, absolutely. So if this didn't work, we could come back and we could either make the footprint of the structure bigger, or we could, by increasing the square meterage of it, or we could increase the depth of it. The storage is shown as being online rather than offline, so basically all the flow from that 0.5 hectares of impermeable area is entering into the structure. Should this structure flood, we would have that information stored in the memory, so there'd be a silo above the ground where the water would rise up above the ground and be remembered, and then be allowed to flow back down into the structure and out through the flow control and out through the base and through the sides of the structure. So storage is online, so the flow is entering into the storage structure and the network and staying within the structure and the network. Offline, we could be taking it out of the system. Okay, so I'll just close the information on. Okay, and I'm going to look at the results here. And what this is showing you is the fact that by producing that rainfall using the IDF information and the CRP at the very outset, what we've run now are a range of events, all for this theoretical 50-year return period, from 50 minutes storm duration all the way up to 10,080 minutes. That's 7 days. So this is a really, really robust test of the performance of your structure. Okay, so it's the 2,160 minute storm duration is the critical one. I'm ignoring all the blue text because the red text is showing me what the worst case is in terms of the maximum depth of water that has risen up from the invert level of the structure. Now remember, the structure is 1 meter deep and the maximum depth of water is 899 millimeters, and the maximum flow that's gone out through the flow control is 4.7 liters per second, because we're a little bit lower than the 1 meter design head, the depth of the structure. The discharge volume is 2,000 cubic meters have been discharged out, and the maximum amount of water that's infiltrated into the ground out of the structure through the base and the sides is 20.6 liters per second. The area time curve comes from the MicroDrainage program. So basically, I will need to show you that in the next webinar, or when I go into the network. I'll show that to you in the network very shortly. It's kind of the obverse of the
time of concentration, which we cover in the second day of training. So what do we need to do to this structure is nothing at all. The maximum depth, the worst case scenario is the water is going to be, it's going to be filling the structure 90%. We could shrink it a little bit. The flow is being controlled to less than our 5 liters per second, and we've got a volume there of 554.8 cubic meters. So we could take that volume from the original quick storage estimate. Remember, we had those huge figures from the quick storage estimate, and there we need to go through the same process for the other subcatchments and design our infiltration trench soakaway or soakaways, swales, etc. in exactly the same way. We are rapidly running out of time, so I've run through one. I could always do another one next time round, but I really want to show you the power of the program and how we can combine these together holistically to see if this is going to work at a catchment scale before we integrate them into the model and make sure we're not wasting our time. So if we click on the next step, imagine we've now designed a range of other structures as well apart from the cellular storage. Let me click on Cascade and you'll see a blank screen. I'm just going to save that previous one out. On this tablet now, I want to load in the structures that I have designed across the development, across the project. And there's a little add button here, a little plus sign. So let me click on this to browse for, well, there's one we've done just now, the cellular #2 structure. I did want to show you something else before I did this really, but not to worry. Let me add in some more. Maybe there's another cellular storage structure that we were working with for another area. Let us add in what's trench soakaway there. So maybe the cellular storage could be linking into the trench soakaway. Let's add in the swale and maybe put that at the head of the system. I'm just going to scope out with these little icons on plan what would be happening across our site. And then finally let me add in a pond, for example. Okay. Now, how will these work hydraulically? Remember we had the results for the cellular storage just now. I could have looked at the graphs and I could have shown you some graphics on the structure itself. But how do they work hydraulically? How do they work in terms of water quality and treating things like total suspended solids, hydrocarbons, and those kind of elements? There is a pollution removal tool, a pollution train that we can use to analyze how each of these structures will perform. So I'm going to do two things. One, click on the pollution train and see how each of these would act individually, but then I'm going to link them together and analyze the gain, if you like, of producing a SUDS train. So if I click on pollution train, okay, that's it. Just fixing the structure, okay, and save that. So these are the individual structures, #2. Okay. So looking at the structures that we had on the tablet, we had 2 cellular storage structures, a trench soakaway, a swale, and a pond. In terms of total suspended solids, in terms of hydrocarbons, how do they perform for water quality? What percentage pollution removal would you gain by putting in a pond? Well, for total suspended solids, between 75 and 90%. However, the downside of using cellular storage structures or culverts or pipes, hard engineered solutions, is that you're not going to gain any water quality benefits in terms of removal of total suspended solids, hydrocarbons, phosphates, nitrates, heavy metals, etc. Whereas these other structures, which are softer solutions that have stone, these have higher pollution removal characteristics available to them. Now what we can do is go back to the cascade and the definition of the cascade, and let us say that the swale at the upstream end is discharging into the cellular storage structure that we designed just now. And that cellular storage structure in turn is linking into a trench, and maybe this other cellular storage structure is also linking into the trench before it discharges into the pond. So this has taken the flow from the flow controls. So remember I put in a hydro brake for the cellular storage number 2, and also analyzing in terms of water quality, the benefits of each of these accumulating. So let's look on the pollution train and save the train results. Now there's only one result, and that is the final discharge from the outfall of the pond. And notice how the total suspended solids figure has really increased now. So the benefits of linking the cellular storage into the trench soakaway, into the swale, or vice versa, and then into the pond, is that we're treating at least 83% of the total suspended solids and up to 93%. We're treating between 60 to 80% of total phosphorus and 40% nitrate. So if you're working in Australia, we have targets on new developments of 80, 40, and 40. So 80% total suspended solids, 40% phosphates, 40% nitrates.
Is there any information or documentation on the difference between different infiltration structures offered? Because they're finding them almost the same. Is there
Any advice on the infiltration structure?
structure to use?
Yeah.
So is cellular storage better because of the better stored volume?
Good. Yeah. Yeah, good. There's another good question that's just come in about right. Yeah, good questions, folks. The questions coming in are: is there any kind of documentation to enable us to make meaningful choices? There are, and normally when I'm doing this on the training, there's a SUDS planner that comes in with the program. I'll show you that very briefly, but there is an option to use the SUDS planner, and in the SUDS manual there is a lot of good experience which will tell you which are the better options to use. The SUDS planner is based on the original SUDS manual C609. How did I draw the link lines? Okay. In terms of the cascade, how did I draw those link lines? If I show you the define, I just right-clicked on this little green arrow. This is the outfall from the structure. So if I right-click, and then drag, and I take it to the inflow, the little blue arrow on the cellular storage structure. Now, apart from running the pollution train analysis, I can now analyze this. Remember the green for go button that I used on the cellular storage structure number 2? I can now analyze this whole SUDS train for the hydraulic performance. So if I click on Analyze, using that 50-year range of events from 50 minutes all the way up to 7 days. So now we are remotely assessing the performance of this potential SUDS train. Now, if it works, great. I know that when I add these structures into the locations of my model, I can guarantee that that model will work, because within the model, you've got the flow conveyance system as well. Okay, yeah, the difference between the cyan and the red arrows, we've got the inflows and the outflows locations of the structures and overflows. There's an inflow into the structure, an outflow out of the structure, and there's an overflow. So what we can do is we can see what's happening there. Look at the impact of us now plugging in another structure and another flow upstream of our cellular storage structure number 2. We've now created flooding. So we'd have to fix this before we move on. I'm going to come down to the bottom. So look at the pond. The pond itself is okay. I could click through the structures. I've got flooding on cellular storage structure number 2. I've got flooding on structure number 1. I would edit these and then fix them before I then put them into the model. But I'm not going to have time to show you within the next 60 seconds. But what I would like to do is show you how you incorporate the structure. So assuming we've fixed that in source control, how do you then add these structures into the fully integrated model? So we've got the flow conveyance structure that we designed last time. How do we add these into the model and integrate them? I'm going to click on one that is incomplete, where I'm showing you that we've got flooding with the flow conveyance system. Specifically at the bottom here, we've got 800 odd cubic meters of flooding on the surface where the pond location is. We've got flooding and flood risk in other areas at all. So let me go on to the plan view and remember manhole number 44, manhole number 7, for example, and let us just add in some of those structures into the model. So if I just zoom into the bottom here, this is manhole number 44. If I right click and look at the properties of this manhole, okay, whoops. Okay. Oh, got some flashes on the screen. I'm going to bring up the toolbox and click on the structures, because I want to now add one I've designed earlier. I've designed an attenuation pond, so I'm left-clicking, dragging, and putting the pond in the pond location. We've got a manhole there, which is a node, a dummy node, a dummy manhole, just to locate and import a pond. Okay, so I'm just going to say, double-click on that, OK to that. Here's one I've designed earlier. Say OK. And now, within the summary of results, how much flooding have we got left? Okay. We've solved the flooding at the pond location. Manhole number 44 has vanished because we've solved the flooding. I could tick on all the information about the analysis of the results, whether there's surcharging, whether the flow is still okay within the pipes themselves. But I'm going to just concentrate by clicking these flags to switch off the OK, switch off the surcharged pipes. So let's just look at those pipes where there is flood risk, where the water is getting close to the ground, and flooding, where the flooding is above the surface of the ground. How we analyze this, I'm going to run through in the 4th of the CPD series. So let us just take a look at manhole number 7 and then add in the cellular storage structure, for example, onto manhole number 7. So if I go to the site option, go to manhole number 7, and then say OK, we're zooming in onto manhole number 7. Just centers it in the screen for me, just makes life a little bit easier. And let us now add, if I hover over these little icons, you can see there's porous car parks, cellular storage, the filter drains, etc., etc. So we design the cellular storage structure, left click, drag it, drop it onto the location of the manhole, and then I could just import our cellular storage structure number 2, and there it is. OK to that, and then look at the results. Everything's gone blank because essentially we've resolved the flooding and the flood risk problems that we had on this site. We still have surcharging and we still have pipes OK, but we don't have any flooding and we don't have any flood risk. So what we have is a fully integrated model showing the flow conveyance, incorporating storage structures, and when you run the analysis, we can show the video outputs. And we can rotate this around and zoom in Remember we identified the crossings and clashings last time. Now you can see the flow going through the pipe network, filling the storage structures and ensuring that we don't have any flooding or flood risk. I'm just going to take the final few questions. So these are the site characteristics of the impermeable area, the limited discharge off the site to ensure that we had no flooding for the 50-year return period. We used the design guide. This is all in the source control module. And we could do this holistically and then incorporate those structures into the model in the knowledge that if they are working in isolation, when you incorporate the flow conveyance system as well, you're guaranteed, assuming you put the structures in the right place, and where you put those structures I'll cover in a little bit more detail next time, because the program will help you identify the obvious locations of these structures. We can then guarantee that your projects will not create any problems because you have the benefit of additional attenuation within the manholes and the pipe network or ditches and swales themselves. So thank you one and all. Take care, and feel free to email me. My email address is at the bottom of the screen, peter.coombs@xpsolutions.com, and look forward to hearing from you soon. Take care. Bye for now.